first question, how to draw pressure, volume and temperature entropy diagram for reheat Rankine cycle. Second question, solve one problem on reheat Rankine cycle by using Mollier diagram and steam table. Let us understand how to draw pressure, volume and temperature entropy diagram for reheat Rankine cycle, which is thermodynamic vapor cycle. As this is the thermodynamic vapor cycle, steam is used as a working substance. If we observe the diagram, here is boiler, high pressure turbine, reheater, low pressure turbine, condenser and pump are the main components through which the working substance is passing when the different processes are taking place. Now we will consider the initial condition of the working substance. We will consider 1 kilogram of saturated water is entering inside the boiler at pressure P1, volume V1 and temperature T1. So we will show this point 1, that is the initial condition of the working substance on the diagram. So at the entrance of the boiler I will indicate here the point 1. Then on the pressure volume diagram, suppose here is the point 1, then pressure P1 and volume V1. Then for the temperature entropy diagram, here is the saturated liquid line and this is the saturated vapor line. Now the condition of the working substance is the saturated water. That means it is in saturated liquid phase. So we have to show point 1 on this saturated liquid line. So I will show here point 1 with temperature T1 and entropy S1. Now we will move for the different processes. So process 1 to 2 is the heat addition at constant temperature and constant pressure. So this heat addition process is taking inside the boiler and here will be point 2. Now one important point is that when there is reheat Rankine cycle, we have to convert the saturated water into superheated steam. So point 2 we have to indicate for the superheated steam. So how to draw pressure, volume and temperature entropy diagram? Because we have to keep temperature constant as well as pressure constant. So when the heat addition process is taking place, volume is getting increased as well as entropy is also getting increased. So for the pressure, volume, I will show here 1 to 2. So here will be point 2. Then for the temperature entropy diagram. So as we add the heat to the saturated water, then its phase is getting changed, and due to the phase change process, temperature will remain constant and saturated water is getting converted into dry saturated vapor. So I will show with constant temperature, here will be point. Now when it is getting converted into dry saturated vapor, we have to continue to add the heat because we have to generate the superheated steam. So what is happening? So after dry saturated vapor, if we continue to add the heat, then its temperature is getting increased as well as entropy is also getting increased. So we have to show here with increase in temperature as well as increase in entropy. So here will be point 2. So this point 2 is nothing but it is for superheated steam. So I will show here, that is T2. So T2 is for superheated steam and here is the entropy S2. Now what is the heat absorbed during the process 1 to 2? So I will show arrow also. So this heat absorbed is nothing but the change in enthalpy. So we have to take the enthalpy at point 2 minus enthalpy at point 1. So I will say heat absorbed is equal to H2 minus H1 during the process 1 to 2. Now we will move for the next process. So next process is process 2 to 3. Now this is carried out in the high pressure turbine. Now for this high pressure turbine, I will say here is the inlet point and here is the outlet point. So I will show here the point 3. Now what is the process taking place? So this is isentropic expansion in high pressure turbine. That means entropy will remain constant and expansion process is taking place. So what is the effect of expansion? So we know that when the expansion process is taking place, its pressure is getting decreased. Then volume is getting increased, and as the pressure is getting decreased, temperature will also getting decreased. Now this is the superheated steam, and when this expansion is taking place here at point 3, dry steam is generated. So we have to show this expansion only up to this dry saturated vapor. So we have to take the point 3 on this line. Now we will show this process. And now pressure is getting decreased, volume is getting increased. So I will show here. So here will be point 3. I will show arrow also. Now for the temperature entropy remain constant, and the superheated steam is getting converted into dry steam. So entropy remain constant, temperature decreases. So again I will show this. So here will be point 3. So if we observe S2 is equal to S3. Now what is the work done during this process? So because when the expansion is here, the partial expansion is carried out. So due to partial expansion, work done is there. So our work output is there. So here are two-stage expansion process is there. So this is the first stage. So I have written here work done 1 to the suffix 1. So what is the work done 1? So that is nothing but the change in enthalpy. So again we have to take here the change in enthalpy. So here I will say temperature T3 is there. So H2 minus H3. So we have to write here H2 minus H3. Now we will move for the next process, that is the reheating of steam at constant pressure. This reheating process is carried out by using the heat from the boiler. So here we have to show here process 3 to 4. Now one important point is that we have to increase the temperature of steam from point 3 to 4 in such a way that temperature at point 4 is equal to temperature of superheated steam. Now if we observe this diagram, temperature of superheated steam is at point 2, that is T2. So we have to take T4 is equal to T2. So we have to show here T4 is equal to T2, and this process we have to take at constant pressure, that is pressure at point 3 is equal to pressure at point 4. So what is the effect of this reheating on other parameters? So when heating is there, then the volume is getting increased as well as entropy is also getting increased. So I will show this process. So pressure will remain constant. So P3 is equal to P4. So I will show here point 4. Then we have to indicate here P3 is equal to P4. Now for the temperature entropy diagram, we have to take temperature at point 4 is equal to temperature at point 2, and entropy we have to use the increase in entropy. So I will take the horizontal line here, and on this horizontal line only I will select here the point 4, and there is the increase in temperature. So we have to take here the inclined line. I will join this line. Now if we observe T2 is equal to T4. So all the conditions are getting satisfied. So what is the heat absorbed during this process? So heat absorbed is nothing but the change in enthalpy. So enthalpy at point 4 minus enthalpy at point 3. So H4 minus H3. Now after reheating, if we observe, if I show arrow, then there is the low pressure turbine. So again, which process is carried out? So isentropic expansion in low pressure turbine. So process 4 to 5. So at the outlet of low pressure turbine, I will show here the point 5. So how this isentropic expansion process is carried out? If we observe here, entropy will remain constant. Then due to expansion process, pressure is getting decreased, volume is getting increased, and temperature is also getting decreased. So we have to show all these processes. Now I will show here decrease in pressure but increase in volume. So first I will indicate here the volume at point 4, that is V4. Then here will be volume at point 3, that is V3. Now I will show inclined line. So here will be point 5. So here is volume V5 and pressure is nothing but P5. So this process is carried out. Now how to show 4 to 5? Now here this is the superheated steam. So it is getting converted into wet steam. So if I show here the constant entropy line, then decrease in temperature at the same time entropy remain constant. So I will show here the 0.5 and here is the temperature T5 and entropy S4 is equal to S5. S4 is equal to S5. So this process is getting completed. Now due to isentropic expansion by this low pressure turbine, some work output is there. So what is the work done? So this is the second stage. So I have written here the work done to the suffix 2. So for the second stage, how I can write? So again here is the change in enthalpy. So what is the change in enthalpy? So here H4 minus H5. H4 minus H5. This is the change in enthalpy, is nothing but the work done, that is at the second stage turbine. Now again we will move for the next process. So next process is carried out in condenser. So condenser heat rejected. So this heat is rejected at constant temperature and constant pressure. So we will show here process 5 to 6. Now what is the effect of on other parameters? So we have to keep pressure constant, we have to keep temperature constant. So when the heat rejection process or cooling is taking place, volume is getting decreased and entropy is also getting decreased. Now here at point 5, if we observe here, condition of working substance is wet steam, but after cooling it is getting converted into saturated water. So we have to show 0.6 on the saturated liquid line. So in the same way I will show here 0.6 with constant pressure. So volume is getting decreased. So here will be 0.6 and volume V6. And for this temperature entropy, we have to extend this 0.5 up to the saturated liquid line. So here will be 0.6. So T5 is equal to T6 and I will show here the entropy at 0.6, that is S6. Now what is the heat rejected during this process? So heat rejection is nothing but the change in enthalpy. So we know that here cooling process is taking place. So we know here the enthalpy at 0.5 is more than the enthalpy at 0.6 because 0.6 working substance is cooler than the 0.5. So we have to take H5 is more than H6. So we will take H5 minus H6. Now we will move for the process 6 to 1. So here is the pump. So what is the function of the pump? So by the pump, the saturated water, so here is the saturated water is carried out to the boiler. So here is the work input and this work input is known as the pump work. So here pump work is there during the process 6 to 1. So this saturated water is just carried out to the boiler in the same condition, that is the initial condition is saturated water. So how we can show this? So we have to show the 0.6 to 1 along with saturated liquid line. and work input is there, so it is the same case as some heat supplied or heat absorbed is there. So what is the effect of heat absorption? So due to heat absorption, temperature is getting increased because some work is given. That means its a temperature is getting increased, pressure is getting increased, and the volume is getting decreased. So we have to show, so from point 6 to 1, pressure is increased, volume is decreased. So we will just join these 2 points. That is P1 is greater, P5 is equal to P6 here. So P1 is greater than P6. And now we have to show this temperature entropy diagram along the saturated liquid line. So I will join these 2 points along the saturated liquid line, because when the working substance, that is saturated water, is passing through this pump, its a phase remains constant. So here is the diagram. Now pump work, how we can write this? Now pump work is nothing but we have to take the change in enthalpy. So enthalpy at point 1 is more than the enthalpy at point 6. So I will write here H1 minus H6. Now we have to write this in other way. So this enthalpy we will write in terms of the specific volume as well as in terms of pressure. So how we can write this? So this is very important. So we have to take the specific volume at the condenser pressure. So this condenser pressure, that means lower pressure, and it is at P5 is equal to P6, because 0.6 is at the condenser pressure. So we have to take the specific volume at condenser pressure. So I will write here V, and now we have to take the change in pressure. So multiplied by the change in pressure in between these 2 points 1 and 6. So we can take here P1 minus P6. So I will write here P1 minus P6. So how we will define this P1 and P6? So P1 is the boiler pressure and P6 is the condenser pressure. Now we will understand some formulas with the help of this diagram. First is total heat absorbed. Now if we observe this process, then the heat absorbed is during the process 1 to 2 as well as process 3 to 4. So this heat is getting absorbed by the working substance from the boiler. So how we can write this total heat absorbed? So during the process 1 to 2 we have to take the change in enthalpy, that is H2 minus H1, plus during the process 3 to 4. So here is the process 3 to 4. We will take the change in enthalpy, that is H4 minus H3. So this is the total heat absorbed during the whole reheating process. Then we will move for the heat rejected. So heat is rejected during the process 5 to 6. So here is the process 5 to 6. So again we have to take the change in enthalpy. So we have to take H5 minus H6. Now next is pump work. So pump work here is the during the process 6 to 1. So again for the process 6 to 1 we have to take the change in enthalpy, that is H1 minus H6. So we can write this formula in other way by using the specific volume. So we have to take the specific volume at point 6, that is at the condenser pressure. So here at point 6 there is the condenser pressure. Now if we observe what is the phase of the working substance at point 6, so it is at the saturated liquid line. So we have to refer the specific volume for the liquid, that is for the suffix F from the steam table. So we will use here at the condenser pressure value of Vf. So we will write Vf multiplied by the difference in temperature, difference in pressure in between this 0.6 and 0.1. So at 0.1 pressure is P1 and at 0.6 pressure is P6. So we will take P1 minus P6. Now we will move for the next, that is what is the net work done. So we will take this net work done, or we will calculate this net work done by 2 ways. So first way, we know that work done is equal to heat absorbed minus heat rejected. So here is the heat absorbed, we will take as it is, minus heat rejected. So here is the heat rejected, we will take as it is. If we simplify this, then minus sign we have to multiply inside the bracket. So it will be H2 minus H1 plus H4 minus H3 minus H5 plus H6. Now what is the second way? So second way, during the expansion process, that is here two-stage expansion is there is some work done, and when we consider the net work done, here is some work input to the pump. That means net work done during the whole process is work done at the high pressure turbine, that is work done 1, plus work done due to low pressure turbine, that is work done 2, minus we have to take this pump work, that is work input is here for the pump, and we have to subtract this. So what is the work done 1? That is during the process 2 to 3. So again we have to take the change in enthalpy, that is H2 minus H3. Work done 2, that is during the process 4 to 5. So again for 4 to 5, H4 minus H5 minus pump work. So pump work is during the process 6 to 1. So again we have to take difference H1 minus H6. Now we will simplify this. H2 minus H3. So here I have rearranged this in this way. So here is H2 is there minus H3 plus H4 minus H5 minus H1. So minus we have to multiply here inside the bracket, minus H1 and minus minus plus H6. So if we compare these two, both are same. So we can either use this formula or this formula. Now we have to calculate what is the efficiency of reheat Rankine cycle. So again same formula is there. So we know that efficiency is nothing but work done by heat absorbed. So this work done is nothing but W net that we have to take. So W net divided by heat absorbed. So what is this W net? So again we will use this heat absorbed minus heat rejected. So if I write here heat absorbed minus heat rejected, then we will simplify this. That is heat absorbed is getting cancelled. So 1 minus heat absorbed, that is 1 minus, in the numerator there is heat rejected. So 1 minus heat rejected divided by heat absorbed. So again we can use either use any one formula, that is W net by heat absorbed or 1 minus heat rejected by heat absorbed.
Now we will solve one problem. Steam power plant operates on theoretical reheat cycle. Steam from boiler at 150 bar and 550 degrees Celsius expands through the high pressure turbine. It is reheated at constant pressure of 40 bar to 550 degrees Celsius and expands through the low pressure turbine to a condenser pressure of 0.1 bar. With the help of Mollier diagram, find out first pump work, second turbine work, third net work done, and efficiency of the reheat Rankine cycle.
This is Mollier diagram. On vertical line, enthalpy H in kilojoule per kilogram is given. On the horizontal line, entropy S in kilojoule per kilogram Kelvin is given. These blue lines for the pressure line, and pressure is given in bar. These horizontal green lines are the temperature lines, and temperature is given in degrees Celsius. This dark red line is the saturation line. Now, if we observe the given data, then the steam from boiler at 150 bar and 550 degrees Celsius enters in high pressure turbine. So at the entrance of high pressure turbine is the point 2, and we have to select the point 2. Now pressure and temperature is given. So if we maximize this diagram, here is the 100 bar and here is 200 bar. So in between them there are total 5 lines. So here first line is for the 120 bar, then 140 bar and 160 bar. So in between 140 and 160 bar there is one middle point, that is for 150 bar, and temperature is 550 degrees Celsius. So this green line is for 550 degrees Celsius. So here is the point of intersection, and this point of intersection is nothing but the point 2. So we will write here this is the point 2. Now we have to find out what is the enthalpy at this point 2. So how to find out this enthalpy? So we will select here one line and we will draw one horizontal line from this point 2 on this enthalpy line. So what is the value for this point? That is the point of intersection, that is enthalpy H2 is 3450 kilojoule per kilogram. So we have to note down this value. Then what is happening in high pressure turbine? That is the expansion is taking place, and after the expansion pressure that is equal to 40 bar. So we have to show this isentropic expansion. That means entropy will remain constant. So again we have to select one line and we have to ex extend this point to up to 40 bar. So here is the line for 40 bar. So here is 10 bar, here is 20 bar, and after 20 bar, here is 50 bar. That means this line is for 30 bar and this inclined blue line is for 40 bar. So for this point, we have to extend this point 2. So I will extend this point 2 up to this 40 bar. So here is the extension point. Now, again at this 40 bar, what is the temperature? So if we observe here, this is the extended line, and at this line temperature is 335 degrees Celsius. That is it is below this 350 degrees Celsius, this point. Then temperature is 335 degrees Celsius that we have to note down. And what is the enthalpy? So again for enthalpy, I will extend this point 3. And if we extend this point 3, we will get the value. So what is the value? That is, if we observe here, it is above 3000, that is 3052 kilojoule per kilogram. Now we will see, this is selected point is point 3. So we will write here, this is the point 3. Now next it is given that it is reheated at constant pressure 40 bar and 550 degrees Celsius. So during reheating, pressure is given 40 bar. That means this pressure will remain constant. This is the line for 40 bar. And temperature is also given, that is 550 degrees Celsius. So we have to again select one point for this given pressure and temperature. So here this is the line for 40 bar. And temperature is given, that is 550 degrees Celsius. So this point after reheating, that is the point 4. So we will write here, this is the point 4. Now for this point 4, what is the enthalpy? So enthalpy at this point 4 is nothing but H4. So we will select here one line. We will extend one line from this point 4. And what is the value? That is, it is above 3500. So its the value is 3560 kilojoule per kilogram. And we have to note down this value. Now again, in low pressure turbine, it is expanded. But this expansion is isentropic expansion. And it is expanded only up to 0.1 bar. Now, if we observe, here is 0.1 bar. So, we have to expand this. That is, we have to extend this line from this point 4 to 0.1 bar. So, again, we will select here one line. So, we will draw straight vertical line. And here is the point of intersection. Now this is the point of intersection and this point is nothing but the point 5. So again we will write here, this is the point 5. Now for this point 5, again we have to find out what is the enthalpy at this point. So how to find out? So again we will draw here one horizontal line, and what is the enthalpy? So if we observe, here is 2000 and here is 2500, that is here is 2100, 2200, and here is 2300. So H5 is equal to 2300 kilojoule per kilogram. Now what is happening in condensation process? So this condensation process, it is taking place, that is after condensation there is 0.6, but this condensation is taking place at constant pressure. So pressure at 0.5, that is 0.1 bar, is equal to pressure at 0.6, that is P6 is equal to 0.1 bar. And at this point, by using steam table, we will find out the specific volume. So specific volume for the saturated water or saturated liquid, Vf is equal to 0.001010 meter cube per kilogram.
Now we will move for calculation. We will first calculate what is the pump work. So we have to take here difference in pressure, that is boiler pressure and condenser pressure. And remember one thing, that is we have to take this pressure in kilopascal. So pressure is given in bar. So 1 bar is equal to 10 raised to 2 kilopascal. And we have to multiply this difference in pressure with specific volume for the saturated water, or we can say saturated liquid at 0.6. So this Vf we have to take, and we have to take this value from the steam table. So pump work is equal to 0.001010 multiplied by, in the bracket, 115 to 10 raised to 2 minus 10, and which is equal to 15.14 kilojoule per kilogram. Now we will calculate the turbine work. So here we have to add the work done in the high pressure turbine as well as low pressure turbine. So we will take the values, that is 3450 minus 3052 plus 3560 minus 2300. And answer 1658 kilojoule per kilogram. Now we will calculate what is the heat absorbed. So in this reheat Rankine cycle, heat is getting absorbed in boiler as well as when the steam is getting reheated. So we will put the value 3450 minus 206.97 plus 3560 minus 3052, which is equal to 3751.03 kilojoule per kilogram. Now we will calculate the net work done. So net work done is equal to turbine work minus pump work, and which is equal to 1642.86 kilojoule per kilogram. Now we will calculate thermal efficiency, that is the reheat Rankine efficiency. So this reheat Rankine efficiency is equal to net work done divided by heat absorbed, and which is equal to 0.438. Now we will convert this value in percentage by multiplying with 100, which is equal to 43.8%.